This problem here is the statement is longer than actually its difficulty is, because it's just given, we're given a poset, right, with a given order relation that is described with this Hasse diagram here. And then we're given a subset, which is this one, right? We have to describe notable elements of this set, right? And then answer a few questions about this. So let's begin with the first, right? The first is, we're asked which elements of S are maximums, minimums, minimum, maximum, supremum, infimum, etc., right? Okay, it's clear that the maximals of S are, well, it's only one, it's G, right? G is the only element that has none that is above it, right? In the set S, which is this one, right? The set S. And minimals, of course, minimals are those elements which have none below, and these are these three elements, right? So it's I, H, I, and J. Okay, these are the maximums and the minimum. About the supremum of the set, well, clearly the supremum is G, which is also a maximum because it's part of the set, right? There is no infimum, and the reason is this, the set of lower bounds of this set is empty, right? There are no lower bounds. I mean, there's no elements here in the set A that are smaller than or equal to every element of the set S. Not even this one, because this one is smaller than this and this, but it's not smaller than H. And clearly, neither of these is a lower bound, because, for instance, H is not lower than I. So there are no lower bounds for this set, so, and therefore there is no infimum. And of course, there's no minimum, right? So this answers already A. Now, question B is about a question about K, this element here, okay, K. And the question about K is whether this is an upper bound. Well, of course it's not, right? Because this is smaller than this element here, which is in the set, so it's not an upper bound. So K is not an upper bound. Not upper bound. All right? Then what about C? Let's see, where is C? C is here, okay? Let's see if C is an upper bound. Well, is every element smaller than C? Well, obviously all these three elements are smaller than G. So all we have to check is whether this element is larger than G. But it clearly is, because there is a line going up, right? A path going up, joining G with C. So C is an upper bound. Is an upper bound. All right? That answers B. Now C, is A totally ordered? No. The answer is no. A totally ordered set can be represented in a line. All the elements in a line, well, in a vertical line if you want to represent the Hasse diagram, right? And this is clearly not the case. So, well, you can see, for instance, that I and J, H and G and I are not comparable to each other, right? Neither this is smaller than this, or this is smaller than this. So it's not a totally ordered. Not totally ordered. And the last question is R a well ordered in A? The answer is no, it's not. It's not a well ordered in A, well, for several reasons. First, because every well order would be a total order, and it's this, and R is not a totally ordered. R is not the total order on A, right? But also you can see it clearly. I mean, look at the set S here. If this R was a well order, that would mean that this set should have a minimum, and it doesn't, right? It has no minimum, so it's not a well order.